Hey, what's up, guys? Chung here again. And today I want to talk about this LeetCode problem number 871, minimum number of refueling stops. This is a hard problem. Yeah, I like this problem. Okay, a lot. So a car travels from a starting position to a destination which is target miles east of the starting position. Along the way, there are like gas stations. Each gas station's station I represents a station that is a station. Basically, as you can see, this gas station is like it has two elements here. Basically, the first one is the location, and second one is the gas. That's what in each of the station object here. The first one is the location of this gas station, and the second one is how many gases we can refuel in these stations. And then it gives you two variables. First one is the start fuel, and you start at position 0 with this starting fuel, starting gas, and then it asks you what's the minimum gas, what's the minimum refuel, the minimum number of refueling at all the gas stations to be able to get the target. If you are not able to get to the target, just return -1. Okay, so for example, a few cases here. So the target is 1 and starting fuel is also 1 and the station is 0. So this means like since we have a start fuel is equals to 1, the basically with the starting fuel we can reach the target. That's why the output is 0. And another example here. So we have a starting fuel is 1, but the closest station is at 10. So which means with the starting fuel, we cannot even get to the first station, um, let alone go get to the target. That's why we return -1 here. And example 3 here, starting with 10. So this is 0, this is 100, right? At the 0 here, we start at 10, so which means we can't get to the first station here, which is 10, right? And at 10 here, we have to refuel, right? And after we refuel 10 with 60, then we have 70, right? So with 70 total gas, we can just pass the 21, 31. There's a 21, right? 21, 31. Then we can get to the 61. And then at 60, we just do another refuel. Then we have a total at 11, 110, which is greater than 100. That's why then we can get to our target. Basically, we just need to refill twice, once at 10 and second one as 60. Okay. Mm, so so basically that's the question. And so how should we approach to the solution, right? I mean, for me, personally, at the beginning, I thought, okay, I was like, this seems like a DP problem because I was like, I was trying to, define like a DP based on the ask itself. Basically, I'm trying to define like as a DPI, right? So the DPI, I was thinking of, okay, can I use DPI to represent the minimum number to refuel when we reach the station I, okay? And then I realized that, okay, so for that to work, I mean somehow we have to somehow we have to uh, come up with a state transition function somehow from I minus one, right? Or I minus two, whatever it is. But to be able to, I mean, to get from the dpi minus 1 state to dpi, we have to somehow, I mean, knows what's the gas, right? How many gas we have at dpi minus 1, right? Because if the remaining gas at dpi minus 1 is not enough for the car to travel to the dpi, then we cannot get dpi from dpi minus 1. And then I was like, for the gas, what can I do with the gas, right? Can I make a secondary dp, secondary like a dp array here, so that on the second one I just store the gas? But then I was like, I saw this one here. See, the gas, it feel it's like it's a huge number here. So which means there's no place for us to allocate us another space, a dimension just for the gas, right? Because that would definitely, I mean, overflow the memory itself. So which means it's not feasible for us to store that, what's the the start or the current location, or how many fuel left in this DP array. So that's why this this state transition function will not work. And then what's other options do we have, right? And then instead of getting the minimum numbers to be stored in this DPI, what we can store is we can store with DPI here, right? What's the farthest location this I mean it can travel to, right? And then with that, I mean basically I'm trying to define like a 2D array here, 2D DP array. So I and J. Okay. So I means uh at the first I stations, and at the first I stations, if we refuel J's station, what's the farthest place we can get to? Okay, basically within first I stations. Okay, I mean we refuel J times the farthest place we can get. Okay, so when you guys see this definition, did it remind you of anything? I mean, if you guys know the knapsack DP concept, so you might find some similarity between this one and that one. Basically, this problem, at least for the DP solutions, it's like a variation of the knapsack backpack problem. You know, so for in that knapsack backpack problem, so what do you have? You have a backpack, right? You have a backpack with the with capacity W, right? And then you have a bunch of items. Okay, you have a bunch of items, and then each item has its own weight and the value, right? And it asks you with this capacity uppercase W, what's the maximum value you can put, right, into this backpack. So and when you convert that concept into this problem, basically that's capacity, right? The capacity is the is how many stations, we can refuel. I mean, it's the yeah, and then the value in this case is the fuel itself. Basically, the max value in our case is like the farthest place we can go, right? And so yeah, because I think as long as you can come up with this like kind of the farthest place we can get with this kind of within the first few items, uh, what's the with this kind of numbers, exact numbers among those few items, what's the biggest number we can get? That's basically a typical K-knapsack problem, and we can utilize the pattern the template from K-knapsack to solve this problem. And yeah, and so once we have this like DP arrays calculated, all we need to do is that, I mean, we already have this kind of by the time, and then all we need to do is we just need to do a for loop here. We for loop everything. We loop we for loop all the dpn, dpn, and then nj here. N is fixed. We just find the first one who's the farthest place, the farthest place they can go is is either equal or greater than our target. Then this j is our result. Okay. Mm, okay. So let's try to code these things up. Mm, okay. So first we need to define like a number, then get the numbers of total stations here. Okay. And then I'm gonna create a 2D DP here. Sorry, 0 n plus 1 for in range n plus 1. Okay, and the main logic is basically we simply do a since our definition for the DPI and J is the total, the first I stations, and how many stations we actually refueled, right? So 1 equals to n plus 1 because I means the number of the stations. Okay, and then for J means the how many stations we actually refueled within that I station, right? That's why in range uh, we also start from 1 to basically to I plus 1, right? Because for the 0, I mean, if we don't fuel anything, basically that's why I'm gonna do a pre-process in the range of n plus 1. Okay, so one of the base cases is when j is equal to 0, right? So I equals to 0. So what does this mean? So it means that we don't refuel anything. We don't fuel any of the we don't refuel at any of the station, right? In that case, the farthest we can go after, it doesn't really matter after how many stations, because we never refuel. It's always what? The start fuel, right? Because that's as far as we can get without refueling at any station. And that's our base case. Okay, since we have already processed j equals 0, and that's why we can process from j equals to 1, right? And then, so remember, so this dpij means the um, at at the current I, right? At the since we already got I here, right? At the current I here, um, if we the j after filling j's time, right? At j stations. So basically, with k knapsack, right? So we have two options at each state. We either fill at this station, or we don't fill. Okay. Mm, so which means, right? Which means at this I here, and basically if we don't fill, okay, if we don't fill at this station I, right? Then the farthest we can go, or the maximum, gas we can have is what? Is I minus 1. That's the last station, from the last station, right? And the filling the field the refuel time is still j's time, right? Because that's we can always choose if we want to refuel it or not. So, and in this case, it doesn't really matter if we can actually really get to this dpij from the dpi minus 1j, because regardless of if we can get really we can actually get from the station I minus 1 to I, this dpij should still be the same as this one. I mean, assuming we're not going to refuel at this current station I, right? And because that's for each j, right? For each of the j here. Since we're like basically we're looping through all the options here, all the j's options. Basically from 0, from 1 to the current I, we loop through, we try all the possible ways, right? For the dpij. Okay, so the first one is not refuel at the current I, and the second one is to refuel at the current I station. But in order to refuel at the current I station, one of the prerequisite is this car needs to be able to get to the current station first, right? Then how can we know if the car can get to the current station, right? So since we're defining the dpij is the farthest place they can get here, right? So all we need to check is if from the previous station, right? And since we decide to fill at this position at this station, that's why at the previous step will be from the previous station, and the field number is j minus 1. If that's the farthest one can get, if that farthest place is equal greater than the current station is I minus 1, right? I minus 1 dot 0. That means, okay, we can get to the current station. We can get to the current station with this state, from this state. Okay, and only then we update ij, okay, with maximum dpij, right? With what? With the uh okay, with basically with this one plus the current station's gas, okay, right? Basically that's not refuel at current station, right? Here is that refuel at current station, right? Basically for each of the step here, we have to consider that we always need to consider these two options. We either not refuel at the current station or refuel at the current station. And after that, all is left, like I said, we just need to loop through the DP here. Range n plus 1, right? From 0 to n plus 1. If the DP n, since the reason we're going to always fix n here is because we just need to know, right? By the time we have already traversed all the stations, what's the minimum? What's the minimum refuel we need to take whose farthest place can travel is greater than the target? Then we simply return the I, right? Otherwise, -1. Okay, let's try to run it. Okay, cool. See, it barely passed, right? Barely passed. And you know, there is another way, like I think another way you can, okay, so for the space complex, sorry, the time complexity for this solution is obviously n square, right? And then the space complexity is also n square because we have a 2D array here. I believe there's a, like a, a, a improvement where you can improve the space complexity from n squared to n. That's, I mean, somewhere here, basically you have to traverse this thing, I mean, in the in the opposite way, but I'm not 100% understand that solutions, because that's why I'm just only introducing this like basic knapsack like template for you guys to try to understand how can we solve this problem in a DP manner. Okay, and yeah, basically that's a DP. And for okay, basically we are converting this problem. Instead of getting the minimum number at each station, we're converting this DP definition to the farthest place it can go by traveling to the ice station, which we have filled J's time. Okay, and then every time when we add like at each of the station here, we can always do a we can because at each station here, right? At each station, we will try to basically recalculate this I and j. Yeah, basically what we're trying to do here is for each of the station. Okay, and we will try for current station, we'll try it for all the j's possibilities, right? If we refuel at this current station, or we don't refuel, and among all those possibilities, we get the maximum from them, right? Yeah. And in the end, since we already have like all the data we need, all we need to know is the after traveling to the last stations, uh, we just need to find out the first element, whose furthest place can get is greater than target. Then that's our number. Okay, I think that's for the DP problem. And now there's like another more efficient way for this solutions, which is it's a greedy algorithm by using the priority queue. And okay, I will try to explain this to you guys. Basically, the idea for that is, let's say we have a like a zero, and we have a bunch of like a station here. Okay, so let's say our start field is 50. Okay, and let's say we have 50, and here is like uh 50. This is like 10 and 20, right? That's the location of each station. Basically, with a starting field at 40, we can reach to here. We can reach to somewhere here, and we'll be passing basically two stations. Okay, and then basically the idea of this greedy concept is uh, by the every time when we're able to pass a station, we add that station to the priority queue. And by the time we by the time we cannot reach to the second station, we will try to pop. Basically, we'll try to pop the biggest gas station, or the station has the most gas from the priority queue, and we add that gas to our current location. Basically, in this case, we're at 40, right? And then we see, okay, 40, we cannot reach the to the or let's say the target is 60. The target is 60. So as long as we haven't reached the target, we will try to see, okay, so can we include any of the stations with our current, with our new location, right? If we can, we just add it to the priority queue. In this case, it's going to be 10, 20, right? And now we're at 40. So the 40 is still less than 60. So in this case, that's why we need a priority queue, because the priority queue will always maintaining, basically it's a max queue. So we'll pop this 20 out and we'll add 20 into our current 40. And then okay, with that, now we can go to a little bit further, like 60, and 60 is equal to 60. That's when we stop. Basically, the idea here is that we always try to, since we already passed that two stations, and we always try to fill at the largest station, which kind of makes sense, right? Because if you only have you if you need to fill once, you always want to fill at the at the station that can gives you more gas. Yeah, and we just keep doing that. And then once we have a 60, right? We reach 60 here, and then okay, we see, okay, with 60 we can pass 50 now, right? Then I'm gonna to push the 50 into it, right? And assuming, okay, let's assume this is not 60. Let's say this is 90, right? So, and then we see, okay, so with 60 here, it's still smaller than 90. Now I need to try to do another refuel, right? Otherwise, I cannot get to 90. Then I will try to pop this 50 out, right? So, and okay, so when we return -1, so, and it's very obvious when we haven't reached the target, but the priority queue is empty. That's when we return -1 because we have nothing to refuel, right? There's nowhere we can go but to stop it here. Okay. Mm, yeah, I think that's pretty much the whole idea here. And let's try to implement this. So first, I'm gonna have a priority queue right here, and then the answer is 0. Okay, that's our answer, and then of course, then stations. So like I said, so when do we stop, right? We we stop while the current one. Okay, sorry. So basically the current one is going to be the start field, right? That's our starting point. When the current one is smaller than the target, right? Then what do we do? We first try to add, right? Basically while since we are going to traverse the station by station, we also need to like index to tell us how many stations we have added to the priority queue, right? Basically, while I is smaller than, so this is gonna be our station index, okay? IDX, okay? Smaller than n, right? That's when we stop. And what? And the the stations. You know what? Actually, I'm just calling it I here because I don't wanna write those I long index long variables many times. And this i's location, right, is smaller equal than the current, right? That's what we said. Because with the current place, let's see how many stations I mean we can pass, right? And every time we pass a station, we simply add this. We do a heap push, right? Heap push with the priority queue, and since we're going to maintain like a max heap, and we have to do a minus here, right? And we don't care about the index. All we care is the how many gases we have in that station, right? And don't forget to increase the by 1. Okay. And now we have those stations here. And then okay, so we do a check here. Basically, if not priority queue, because at this moment the current is still smaller than the target. Like I said, if at this place, if the we have nothing in the priority queue, that means we cannot get to the target. We simply return -1. Okay. Otherwise, we do what? Otherwise, we just do we pop. Okay, we pop the we do a heap pop dot pop dot heap pop priority queue. Sorry, yeah, sorry, the -1, right? Since we're storing the negative value here, and then we do answer plus 1. Basically, every time we have a new current, we'll try to see, okay, if the current can include any other stations. If it can, I just do insert into the priority queue. Okay. Otherwise, I check this if it's not if it's empty, I return -1. I return -1. Otherwise, then I try to pop another one from the priority queue, and then every time when I pop a station from the priority queue, I basically it's equivalent to refuel in that station, right? And in the end, simply return answer. Yeah, I think that's pretty much it is. Let's try to run it. Start fuel. Oh, I feel yeah. Cool. As you guys can see, this is much faster. Why is that? Because the time complexity for this algorithm for this solution uh is n. First, we loop through all all the stations, right? It's n times, and the operation to do a heap push and heap pop is log n. Okay, so from n square, now it becomes n times log n, and the space complexity is O of n because we only need one list to store at up to n's element. Okay, that's why this greedy algorithm is much faster than the DP problem. Yeah, so I mean, it's up to you guys, right? Which one is easier for you to understand? I mean, for me, this DP solution is absolutely good to learn because not only it will tells you how to define solve this problem in the DP way, but it also help you understand the knapsack problem better. So I would basically recommend you guys try to understand this DP concept, and also if you guys have some interest, want to spend more time on it, try to also understand the knapsack problem more. Yeah, and other than that, this is just I mean a um, a genius way to use greedy technique to solve this problem. Basically, every time when you don't have any state, when you run out of the gas, basically every time when you run out of the gas, you want to pick up from your storage, right? Storage, you want to pick the biggest gas can and put the gas into a tank, and then you keep driving, right? Until you can reach the target. That's then the answer will be the minimum time you need to refuel, right? Yeah, anyway, so two-way solution, two solutions, two ideas, and a great problem. Yeah, okay, thank you so much for you guys to watch the video. I hope you guys learned something. At least I learned a lot from this problem. That's why I want to record this video to share with you guys. Okay, let me know if you guys have any questions or suggestions. And other than that, stay tuned, and I'll be seeing you guys soon. Bye bye.